Hello everyone and welcome back to some more reverse engineering. Today we're going to be looking at PyTime 2, the follow-up to the first video I did last time. So we've been given the binary as well as the source code and we can have a look. So similarly it has PIE enabled, and when we look at the source code it's similar to the last one in the fact that we have instead of being given an address in the last challenge where it just prints one out of main, we have to get it ourselves. So everything is very similar except this part here where now it says enter your name, you input something and then it'll print it out and then we're asked to jump to an address. So for this challenge we have to figure out an address of the executable, because PIE, position independent executable, means it's not going to be loaded at a consistent point. And last time we got a leak from running the executable, said hey, main is at this address. This time we have to figure out ourselves. So we can see here that the printf that's used is taken straight from the buffer, which allows us to do a string format vulnerability. So we can have a look here. I've just written a little sample code where it asks us to enter our name and then it'll put here. So with the printf, it's saying, hey, give me 30 pointers and print them out. I've got the program running and debugging over here. So the important thing to note is that because we haven't provided enough arguments to printf, it'll start reading variables off the stack. So I've printed out the stack here and we can see, because with the nature of the stack, we are currently in call functions. So let's have a look. We can see, we can almost imagine to ourselves the sort of stack trace that's going on. So we have main that then calls call functions, which we're inside of at the moment. I have a cool reference picture here I'd like to share that sort of describes it. So we have the initial main, and then instead, in our case, we have this call functions. So we're up here at the moment and the stack point is up the top here. So if we provide, because there's no checking for that printf statement, the values that it'll put and start printing out, because we don't provide them, will be from the stack. So eventually it'll just keep putting values from the stack that'll be printed out. And eventually what we'll land on is there's a base pointer inside our function that says, hey, after you've finished executing, where should I go back to? So let's just examine that. So what we'd expect in the stack trace is that when we go here, call functions and go to jump into it, the value that's pushed onto the stack to return to will be the next instruction. So you can see here that it ends in 29B441. And if we have a look here where the current stack pointer is, if we leak enough of it, we eventually end on it here. So 5EE9A29B441. So this is where our leak comes into play. So we know that if we print enough off the stack, we'll eventually get this address here. And then it's just a matter of offsets, because we know that this is plus 65 from main. And then we can say, oh, what's the offset between main and the win function? So that's all right. We'll continue here. And I've just got a little program printing off to the side here, and we can actually examine it here. So we say offset is 0xd7. And if we look at the solve function here, it is, we take the leak back and minus the offset, which is 0xd7. So that's the difference between the point where we return in main. So it's the difference between this line here and this one here at the very start of win. So now that we know that, let's go and try execute this against the remote. Alrighty, so I've connected up to the remote here, and I just thought I'd show you something that I learned whilst I was doing this. So it was really important that when we go and send our buffer, this can actually cause problems on the remote. So I'll show you here, for example, the one we've been using locally seems to work just fine. But you'll notice that if we run this here, we actually get a seg fault, and it's because we're printing too much out. So what we have to do here is we have to be specific and say we are actually interested in a certain amount of offset of these pointers. So we only print one, but it's the correct offset. So as we saw in the local version, we are after the 18th, index 18, which means the 19th. So if we run this again and we connect to it, we can actually use a proper printf format specifier to say, hey, get me the 19th pointer. So the 19th point, if you take this address, do pointer arithmetic, so you move 8 bytes at a time or whatever, and then say get me the 19th, we can actually print out the explicit one. So now this is similar to what we have with our leak address. So we can take that and we can just run this and just say leak equals this address, leak minus, what do we have, 0xd7, and do the same thing, but just make sure we print it as hexadecimal so we can enter it. And let's give that a crack. And there we go, we jump to our win function and we got it.